The sky is calm now, blue, radiant, almost innocent. But hidden in those tranquil layers of air lies one of the most violent forces nature can summon, the hurricane. When it awakens, it doesn't just rearrange weather patterns. It redraws coastlines, rewrites maps, and reshapes lives. From the deserts of Africa to the shores of the Americas, a single pulse of warm air can become a world-altering storm. For centuries, we've watched these tempests from the safety of distance, giving them names: Andrew, Wilma, Katrina, as though naming could grant us control. But the truth is far more humbling. Each hurricane is a living machine of heat and chaos, a rotating engine that feeds on the oceans themselves. It breathes in water vapor, exhales destruction, and leaves behind silence. A silence that scientists still struggle to fully decode. Across laboratories, satellites, and research aircraft, meteorologists are piecing together a mystery that stretches from the edge of space to the deepest ocean currents. What transforms a harmless tropical breeze into a monster hundreds of miles wide? How does a storm that begins as a whisper over the Sahara grow into a force powerful enough to erase entire cities? And beyond that, what happens when Earth itself turns against its own balance? Because hurricanes are only one chapter in the planet's long history of extremes. There was a time 650 million years ago when Earth may have frozen entirely, an age scientists call snowball Earth. Our world, locked beneath miles of ice, almost lifeless. Yet somehow, from that frozen tomb, life returned stronger than before. Between the fury of storms and the silence of global ice, the Earth has always walked a fine line between chaos and creation. These cycles of destruction and renewal are written deep into its surface, in the scars left by hurricanes and in the stones dropped by glaciers that once reached the equator. This is the story of how nature tests its own limits, and how humanity tries to understand the rules of survival within it. It is a story of heat and cold, of wind and water, of a planet forever reinventing itself. In the next chapters, we'll follow the birth of a storm from a shimmer of heat above Africa to its transformation into a spinning, city-devouring vortex. We'll descend into the eye of a hurricane alongside the pilots who risked their lives for a few seconds of calm at its heart. And we'll travel back in time to an Earth encased in ice, when the line between death and evolution blurred. Every storm tells us something about our world, about the delicate machinery that sustains life and the terrifying power that can erase it in a moment. This is the anatomy of catastrophe, and it begins with a single breath of warm air rising over the Atlantic. Part 1, Birth of a Monster, the genesis of a hurricane. It begins in silence. No thunder, no rain, no roar of wind, only a shimmer of heat rising from one of the hottest, driest places on Earth, the Sahara Desert. Here, in the blazing summer months, the air becomes so hot it starts to lift itself skyward, carrying dust and heat miles into the atmosphere. From this furnace of shifting sand and shimmering light, a small atmospheric disturbance begins to form, invisible to the human eye, but not to the satellites orbiting 22,000 miles above. Meteorologists call it an African easterly wave, a pulse of moving air, born of uneven heat, pushing westward toward the Atlantic Ocean. Most of these waves vanish, dissolving harmlessly over the sea. But once in a while, one finds the perfect conditions, a convergence of temperature, humidity, and rotation, and becomes something far greater. From space, the first signs are subtle. Streaks of cloud twisting into loose spirals, a hint of rotation in the vapor trails. In the control rooms of the National Hurricane Center in Miami, analysts begin to take notice. Their computer screens show a faint storm cell moving away from the African coast. Within hours, the first data flows in barometric pressure, wind speed, humidity. It's weak, disorganized, but it's alive. Chris Landsat, a scientist at the National Hurricane Center, describes this moment as ignition. Understanding how these storms are born, he says, is like trying to catch lightning with a net. The process is delicate, unpredictable, and yet it always follows a pattern. That pattern begins with the ocean itself. The waters of the tropical Atlantic are warm, over 80 degrees Fahrenheit, a vast storehouse of solar energy waiting to be released. As the easterly wave drifts westward, it gathers moisture from the sea's surface. Every molecule of water that evaporates carries hidden heat, latent energy, which becomes the storm's fuel. High above the waves, clouds begin to tower, merging into massive thunderheads. Within them, warm air rises and cools, releasing bursts of heat that drive the system higher still. This rising column of air creates a vacuum beneath it, drawing in more warm air from the surrounding ocean. The cycle accelerates: rise, cool, condense, repeat. And then a crucial threshold is crossed. When wind speeds reach 23 miles per hour, meteorologists give the phenomenon a name: a tropical depression. It's still weak, but the feedback loop has begun. As pressure drops, more air rushes inward, spinning faster and faster. The rotation is no accident. It's a gift from the planet itself. The Earth's rotation deflects moving air through a force known as the Coriolis effect. In the northern hemisphere, it twists storms counterclockwise. In the southern, clockwise. Without this subtle planetary spin, the winds would simply rush inward and cancel themselves out. Over the next 48 hours, the system strengthens. Wind speeds climb past 39 miles per hour. Satellite imagery now shows a distinct spiral, an organized, pulsing structure feeding on the warmth below. It has become a tropical storm. Somewhere in a quiet corner of a forecasting office, a new name is pulled from the list maintained by the World Meteorological Organization. The storm has earned its identity, but names are fragile things for forces like these. The ocean doesn't care for names. It only provides energy. And the energy, as long as the sea remains warm and the upper winds remain calm, flows endlessly into the growing vortex. Within the storm, the air churns violently. Thunderclouds reach 10 miles high. Lightning flickers in their hearts like nervous systems firing inside a living organism. The temperature difference between the warm ocean and the cooling upper atmosphere creates a massive thermal engine, a structure capable of generating more power than all the world's power plants combined. Still, not every tropical storm becomes a hurricane. The ocean must be warm enough. The wind shear, the difference in wind speed and direction between surface and high altitude, must be minimal. Too much shear, and the storm is torn apart. Too little, and it stagnates. But when everything aligns, the system begins to feed on itself with terrifying efficiency. Jim McFadden, a veteran hurricane hunter pilot, once described the moment a storm crosses the line. You can almost feel it in the instruments. Pressure starts to fall faster than the models predict. The walls of cloud sharpen. The storm tightens its grip on itself. You know you're watching something about to wake up. At 74 miles per hour, the transformation is complete. The storm is now a hurricane, a perfect engine of destruction, fueled by heat and driven by physics. From its calm, circular eye to its roaring outer bands, it has achieved a kind of equilibrium, a balance between creation and annihilation. From the Sahara to the Atlantic, in less than a week, a simple wave of warm air has become one of the most powerful natural systems on Earth. And this is only the beginning, because while scientists have mapped the anatomy of its birth, the question that still haunts them remains. Why do some storms grow into monsters while others die young? The search for that answer will take them higher into the atmosphere and deep into the eye of the storm itself. Part 2. Into the eye. Chasing the storm. The radar screens glow softly in the darkened cabin. Outside, the sky is a shifting wall of gray, a living, breathing mass of water and wind. 5,000 feet above the Atlantic, a turboprop aircraft claws through the storm, its wings trembling. Every few seconds, a flash of lightning ignites the cabin windows, revealing the tense faces of the crew. These are the hurricane hunters, men and women who fly directly into the world's most violent weather so that others might live. The aircraft, a Lockheed WP-3D Orion, is built for punishment. Reinforced fuselage, redundant engines, radar domes bolted beneath its belly. It's less a plane than a flying laboratory. Inside, racks of computers hum as they record torrents of data: air pressure, humidity, temperature, wind velocity. At the center console, Flight Director Jim McFadden studies the readings. The storm ahead, newly christened Hurricane Helena, is strengthening faster than expected. The National Hurricane Center has classified it as a Category 2, but McFadden's gut tells him it's already stronger. The pressure readings are falling too quickly. Radar shows a double eye wall. His navigator calls out. That's not good. A double eye wall, an inner ring of thunderstorms surrounded by a second, outer wall, is often the sign of rapid intensification. Inside this structure, the storm reorganizes itself, tightening its rotation, sharpening its symmetry, becoming more lethal by the hour. Let's get the probe ready, McFadden orders. A crewman hauls a cylindrical instrument, a dropsonde, to the open launch chute. It's a small device, no larger than a thermos, equipped with sensors and a parachute. When released, it will fall through the heart of the hurricane, measuring temperature, humidity, wind speed, and pressure every half second. The data it sends back will help meteorologists on the ground understand the storm structure and predict its next move. McFadden gives the signal. The dropsonde disappears into the gray abyss. Moments later, the first readings appear on the monitors. The numbers tumble rapidly: pressure plummeting, humidity near saturation, wind speed increasing with altitude. The storm is deepening. The aircraft pushes farther inward. Outside, the turbulence worsens. The pilots fight to hold altitude as gusts hammer the fuselage. Rain slams against the windows with the force of gravel. Every bolt, every rivet seems to vibrate. And then suddenly silence. They've broken through. Above them, the sun blazes through a perfect circle of blue sky. Below, the sea churns in a vast spiral of white foam. Around them, towering walls of cloud rise like the ramparts of a colossal stadium. This is the eye, the calm center of chaos, where the storm's rotation balances itself in eerie stillness. For a moment, everyone just stares. It's not fear now, but awe. The sheer scale of it defies reason. This, McFadden says softly, is the closest thing we have to looking into the face of a living thing. The calm won't last. Within minutes, the aircraft must punch back through the eye wall to exit the storm. The return flight will be rougher. Winds are stronger on the opposite side, the right-hand quadrant, where the hurricane's forward motion adds to its rotational speed. If the plane encounters a microburst or vertical shear, even the Orion's heavy frame could be torn apart. But this is the cost of knowledge. Every pass through the storm gives scientists a clearer picture of how hurricanes live and breathe. Back in Miami, analysts watch the data streaming in. The numbers confirm what McFadden suspected. Helena's central pressure has dropped to 945 millibars, the hallmark of a Category 4 system. Over 200 miles wide, its winds now exceed 130 miles per hour. Meteorologist Greg Holland studies the satellite feed. The storm's eye has contracted from 30 miles to 15 in just 6 hours, a phenomenon known as eye wall replacement. It's a paradoxical process. As the old inner eye wall collapses and the outer one takes over, the storm temporarily weakens, only to rebound stronger than before, like a predator catching its breath before the next strike. To the untrained eye, the hurricane's spiral bands may look beautiful, hypnotic, almost graceful. But to the scientists watching from orbit, they are reading the anatomy of destruction. Each line of cloud is a conveyor belt of thunder, rain, and energy, pulling more moisture from the sea and feeding it back into the storm's rotating core. Helena now drifts northwest, following the invisible currents of the atmosphere. The trade winds push it west, while a high-pressure dome, the Bermuda High, nudges it north. The balance between these forces will determine its fate. A shift of only a few miles in the upper winds could mean the difference between a harmless turn into the open Atlantic or a direct strike on the U.S. coastline. For the scientists, this is the crucible of their work, forecasting where chaos will land. Back inside the hurricane, McFadden's team completes another pass. A second dropsonde is deployed, this one designed to capture wind speed changes near the ocean surface, the boundary layer where the storm draws its energy. The probe transmits a stream of data until, finally, the signal cuts out, swallowed by the sea. As the aircraft turns home, the crew knows that somewhere below, waves 3 stories high are tearing across the Atlantic, building momentum toward land. What began as a whisper of warm air over the Sahara is now a roaring engine of wind and water, aimed squarely at the American coast. And as meteorologists study the fresh data, a chilling realization takes shape. This hurricane is strengthening faster than their models predicted. The atmosphere has changed. The ocean, too, is warmer than ever recorded for this region. Something in the equation no longer fits. For now, the scientists can only watch as nature accelerates beyond their expectations. The storm has entered its most dangerous phase, one that could rewrite everything they thought they knew about hurricanes. The race against time has begun. Part 3, the engine of destruction. Inside the hurricane's power source, the ocean is boiling, not literally, but in energy. Each square mile of tropical sea contains enough heat to power every city on Earth for a year. Hurricanes are nature's way of releasing that energy, a self-regulating exhaust valve in the planet's climate engine. But when that balance tips too far, what should be a safety mechanism becomes a weapon. At its core, a hurricane is nothing more than a heat engine. It feeds on the difference between the warmth of the ocean and the coolness of the upper atmosphere. The greater that contrast, the more violently the machine runs. Scientists call it a Carnot engine, named for the 19th century physicist who first described how heat could be converted into motion. But where human engines run on gasoline and steel pistons, this one runs on vapor, pressure, and chaos. In the lab at the National Oceanic and Atmospheric Administration, NOAA, meteorologist Robert Rogers gestures toward a digital cross-section of Hurricane Helena. The model reveals the storm's anatomy in exquisite detail. Spiraling bands of thunderclouds, a hollow eye, and a dome of warm air rising through its center. What you're looking at, he explains, is the most efficient heat engine in the solar system. For every bit of energy it takes in from the ocean, it gives back nearly all of it as kinetic power. Winds, waves, rainfall, it's all energy changing form. As warm air rises from the ocean surface, it cools and condenses into clouds. That condensation releases latent heat, which further warms the air, causing it to rise faster. The process feeds on itself, a loop of acceleration. Each molecule of evaporated seawater adds fuel. Each droplet of rain releases energy back into the sky. The result is staggering. A single mature hurricane can release more energy in one day than all the nuclear weapons ever detonated by humankind. But the hurricane's heart is fragile. Its perfect symmetry can be broken by many things: cooler water, dry air, or strong upper winds that tear apart its rising columns. Meteorologists call this wind shear. When shear exceeds 20 miles per hour between the lower and upper atmosphere, it's like snapping the top off a spinning toy. The storm collapses. Helena, however, has found her equilibrium. Wind shear is minimal, and the sea beneath her is warm, nearly 86 degrees Fahrenheit, 2 degrees above average for late summer. This extra heat acts like jet fuel, giving the storm more power to draw upon. Greg Holland, a veteran atmospheric scientist, once likened it to turbocharging a car. When you hit that pocket of warm water, he said, the storm just explodes. You see the pressure drop, the winds ramp up. It's like watching a living thing take a deep breath. To understand what drives this transformation, scientists must focus on one of the least understood regions of all, the boundary layer, that turbulent zone between the sea surface and the air just above it. It's where friction, humidity, and heat exchange combine to feed the hurricane. Flying into the boundary layer is dangerous work. The winds there are erratic, unpredictable. Updrafts can flip an aircraft in seconds. In 2003, during an experiment known as Sea Blast, pilots flew as low as 200 feet into Hurricane Isabel to measure this deadly interaction. They returned with engines coated in salt spray and stories of waves that, looked high enough to scrape the wings. But the data they brought back changed everything. It revealed that the strongest energy transfer occurs not from the ocean's surface alone, but from the breaking waves themselves. The more violently the sea churns, the more water vapor it injects into the air, and the faster the storm grows. Today, researchers use drones and remote aircraft like the Aeroson Mark III to fly these deadly missions without risking human lives. These small robotic planes can stay aloft for 12 hours, sending real-time readings from inside the boundary layer, the hurricane's fueling zone. Their findings confirm what many feared. As global ocean temperatures rise, so too does the efficiency of this heat exchange. Put simply, warmer seas mean stronger storms. Helena is proof of that. Over the past 12 hours, she has crossed a patch of unusually warm water. An eddy spun off from the Gulf Stream. Within hours, her pressure dropped another 15 millibars. The wind field tightened. The eye contracted to 10 miles across, a perfect, deadly vortex. From orbit, satellites capture the transformation in mesmerizing clarity. A near-perfect spiral, white arms curling around a dark, motionless center. Beauty and terror intertwined. Back on land, forecasters race to update their models. The storm's intensification is outpacing every previous simulation. The supercomputers at the Hurricane Research Division struggle to keep up as the input data flood in. Rogers and his team compare the readings from multiple models, the European ECMWF, the American GFS, the Navy's COAMPS, but none fully capture Helena's explosive growth. "This isn't following the script," Rogers mutters. "It's accelerating too fast." The question arises again, why? Why do some storms explode into monsters while others, born under identical conditions, fizzle out? One hypothesis points to microscopic differences in sea surface temperature, mere fractions of a degree that, when magnified across hundreds of miles, alter the storm's internal dynamics. Another suggests that unseen vortices, swirling eddies of air within the eye wall, help focus the storm's energy inward, creating a positive feedback loop. But there's a third possibility, one that unsettles even the most experienced researchers. The climate itself is changing faster than their models can adapt. As Helena spins westward, its wind speeds now exceed 155 miles per hour, the threshold of a Category 5. Every rotation pulls more heat from the ocean and converts it into motion. It is the purest form of power nature can produce, energy without flame, without fuel, without mercy. And as the storm grows, a grim realization spreads among the scientists watching it. They are no longer studying a familiar phenomenon. They are witnessing something new, a storm born of a world that is warmer, wetter, and more volatile than any in human history. The hurricane's engine has evolved, and somewhere in that whirling chaos, hidden within the equations and radar scans, lies a warning about the planet itself. Part 4, The Path of Destruction. Predicting the unpredictable, for all its violence, a hurricane moves with a strange grace, drifting across the ocean like a colossal, sentient being. From space, it appears serene, even symmetrical, a slow spiral of white cloud turning across a blue canvas. But to those on the ground watching the radar, that perfect geometry means danger. It means the storm is organized and unstoppable. As Hurricane Helena sweeps across the Atlantic, the entire apparatus of modern meteorology comes alive. In Miami, the National Hurricane Center glows through the night, a cathedral of screens and data streams. Scientists monitor wind vectors, sea surface temperatures, and the shifting positions of high and low pressure systems that dictate where Helena will go next. Forecasting her path is part science, part art, and part gamble. The rules of motion are clear, but the atmosphere is a living thing, a chaotic system that defies total prediction. Even with today's most powerful supercomputers, the best track forecasts can still miss landfall by hundreds of miles. Chris Landsat stands before the main projection screen, pointing to the glowing tracks fanning out like strands of spaghetti. Each line is a model, each model a theory about the future. The European model predicts a sharp curve north, sparing the coast. The American model sends Helena straight into the Carolinas. The Navy model splits the difference. Landsat exhales. "We're threading a needle in a hurricane," he mutters. Above them, a high-pressure ridge known as the Bermuda High is sliding westward. A vast, invisible dome of sinking air that steers storms like a hand guiding a toy boat. The position of that ridge will determine Helena's fate. If it drifts too far, she'll curve harmlessly into the Atlantic. But if it holds, she'll be pushed straight toward land. To explain the movement of hurricanes, meteorologist Greg Holland once used a simple analogy. They move like corks in a stream. The atmospheric currents push them along, but the cork itself has a will, a bit of spin that lets it steer, ever so slightly, on its own. That will comes from the Earth's rotation and the hurricane's own momentum. As the storm spins, it interacts with the global wind belts that encircle the planet, the trade winds near the equator, the westerlies at mid-latitudes. The complex dance of these forces determines not only where the storm travels, but how fast it intensifies. And Helena is intensifying fast. The latest satellite scans reveal a tightening spiral, a smaller eye, sharper convection. All signs of a storm entering its peak. Its diameter now stretches more than 350 miles. Within its walls, winds howl at over 160 miles per hour. The sea beneath it is heaving, the waves cresting higher than 30 feet. Meanwhile, along the Gulf and East Coasts, the first watches and warnings begin to flash across television screens. Local meteorologists, relying on data from the National Hurricane Center, urge calm but caution. If you're in the projected cone, prepare to evacuate. That cone, the infamous forecast map that widens with time, is both a scientific tool and a symbol of uncertainty. It shows the most likely path, but not the only one. Inside that white cone lies both safety and ruin, depending on where the storm finally decides to turn. In New Orleans, memories of Katrina linger like a scar. The city's levees are stronger now, rebuilt and reinforced, but few residents truly trust them. In coastal Mississippi, families pack cars with water, food, and photos, knowing from experience that possessions can be replaced, but lives cannot. The question that haunts the scientists and the millions watching is the same: where will it hit? Joe Sion, a leading hurricane modeler at NOAA, adjusts a parameter on his computer simulation. He's trying to integrate new data from the boundary layer, the low-level wind measurements gathered by the Aeroson drones. These readings, combined with satellite temperature maps, could refine the storm's forecast track. But the system is volatile. Even tiny changes in the model can alter the outcome drastically. What we're really doing, Sion says, is trying to simulate nature in all her moods. Every layer of air, every pocket of humidity, it all matters. The models crunch numbers through the night. Thousands of processors calculate pressure gradients, temperature differences, and moisture fluxes, running billions of equations per second. And still, the results diverge. Helena is behaving unpredictably, accelerating in bursts, pausing, then shifting direction. The Bermuda High seems to wobble, expanding and contracting like a lump. In this uncertain atmosphere, forecasting becomes as much an act of interpretation as of mathematics. Robert Rogers studies the latest outputs. Our track predictions have improved 50% in the last 20 years, he says, but intensity forecasts, they're still a mystery. We can tell you where a storm will go, but not how angry it'll be when it gets there. That mystery is deadly. Because for coastal cities, the difference between a Category 2 and a Category 5 hurricane isn't just academic. It's the difference between flooding and obliteration. And the storm surge, the hurricane's hidden weapon, is what kills the most. Oceanographer Stephen Baig watches the simulated waves building across the digital Atlantic. 90% of all hurricane deaths come from drowning, he says quietly. It's not the wind that gets you. It's the ocean, rising to take back what it gave. In the Gulf, the tide begins to swell as the storm approaches. The ocean is already responding to Helena's gravitational pull and the immense pressure differential that drives its winds. The right-hand quadrant of the storm, where its rotation and forward motion combine, piles up water into a wall that moves with the storm like a battering ram. By the time it reaches the coast, that wall could be 30 feet high. The race to predict its landfall isn't just about geography, it's about saving time and lives. Every hour of advance warning can mean thousands of people evacuated or trapped. But the atmosphere doesn't care for human schedules. At 2 a.m., new satellite images arrive. The Bermuda High has shifted slightly south. The models converge. Helena is turning toward the Gulf Coast. Its target, Louisiana. And this time, the storm is stronger than anything the city has faced since Katrina. On every monitor, the forecast cone tightens. The dots marking Helena's position pulse red. The countdown begins. The world watches as the storm closes the distance, 300 miles, 200, 100. The radar sweeps faster. The warnings grow louder. But beneath the data, behind the graphs and satellite loops, one truth remains. For all our science, for all our models, nature still decides. And Helena is coming. Part 5. Landfall. When the ocean strikes back, at first, there is only wind. A low, distant moan rolling through the dark. The voice of a storm still miles offshore, whispering its approach. Then, almost imperceptibly, the air begins to thicken. The trees bow, the sea rises, and the world holds its breath. It is just after midnight when the first outer bands of Hurricane Helena hit the Louisiana coastline. Sheets of rain slam sideways against shuttered windows. Power lines sway like skipping ropes in the gale. On the horizon, lightning flashes reveal the churning wall of cloud advancing over the Gulf. A black, boiling mass that swallows the stars. Inside the state's Emergency Operations Center in Baton Rouge, meteorologists and officials hunch over glowing screens. The latest radar loop confirms their fears. Helena has intensified again. The pressure in its eye has dropped to 910 millibars, a sign of catastrophic strength. It is now a Category 5. The storm is 350 miles wide, moving at 12 miles per hour and dragging the ocean with it. To the east, in Biloxi, Mississippi, storm photographer Mike Ty sets up his camera on the second floor of a hotel. He has chased hurricanes for 20 years, but nothing has prepared him for what he sees through the lens tonight. The storm surge is already pushing over the seawall, a dark, rising mass of water swallowing cars, streetlights, and signs. Within minutes, it floods the first floor of the building. By 8 a.m., he would later recall, a car floated right through the lobby. It hit the glass doors, horn blaring, lights flashing, like a ghost coming through the dark. It was surreal, like something alive had entered the building. The storm surge, the hurricane's deadliest weapon, is a wall of water driven inland by relentless wind. It doesn't just flood, it crushes. It moves with the density and momentum of the sea itself, bulldozing everything in its path. Houses disintegrate, roads vanish, entire neighborhoods are erased in seconds. Along the coast, waves rise over 20 feet high, riding atop a surge that itself has lifted the ocean by nearly 30 feet. Boats are hurled inland like toys. Bridges collapse. The air tastes of salt and iron. At 6:10 a.m., the eye of Hurricane Helena makes landfall near the Louisiana-Mississippi border. The moment of impact is deceptive, a sudden calm after hours of terror. The wind dies, the rain stops, sunlight filters through the ragged clouds. For an hour, the eye passes overhead, a fragile illusion of peace. Then the other side of the storm arrives. The winds shift direction, doubling back with renewed fury. Everything that was battered from the east is now torn apart from the west. The debris, cars, rooftops, splintered wood, becomes shrapnel, flying through the air at over 150 miles per hour. In New Orleans, the reinforced levees hold at first. But as the surge channels into Lake Pontchartrain, the water level rises beyond design limits. In two places, the levees breach. The flood rushes into the lower Ninth Ward, the same neighborhood drowned by Katrina 2 decades earlier. Within hours, entire blocks are underwater. Helicopters scramble to pluck survivors from rooftops. Coast Guard boats weave through the submerged streets, their hulls scraping against traffic lights. And still, the rain falls. Meteorologist Ivor Van Heerden watches from a command post as the gauges rise. "It's not just the surge," he says. "It's the duration. The water keeps coming because the storm is moving so slow. It's like the ocean decided to stay." By noon, Helena has pushed 40 miles inland. Power is out across 3 states. The roar of the wind is unbroken, a constant, furious scream punctuated by the groan of collapsing buildings. At the University of Florida's Hurricane Research Facility, Dr. Forrest Masters and his team monitor real-time data from reinforced towers along the coast. Their sensors record gusts exceeding 180 miles per hour, among the highest ever measured on land. "This is beyond Category 5, Masters says grimly. "We're in uncharted territory. Helena is now more than a storm. It's a landscape in motion." Rivers flow backward under the force of the surge. Highways vanish beneath shifting currents. The air itself becomes weaponized, a mixture of rain, sand, and debris slicing through anything that stands too tall. And yet, within this devastation, scientists see something more than chaos. They see the anatomy of the storm at work, the invisible gears turning. The strongest winds are found in the eye wall, the dense ring of thunderclouds surrounding the comm center. Here, air rises violently, condenses, and releases heat, powering the storm like pistons in a vast engine. The hotter the air inside becomes, the faster the winds spin outside. Above the hurricane, at an altitude of 50,000 feet, another process unfolds: outflow. Air rising through the storm spreads outward in graceful arcs, forming delicate, icy cirrus clouds that stretch for hundreds of miles. This outflow acts like the exhaust of a jet engine, venting energy and keeping the system alive. Together, the inflow at the surface and the outflow aloft form a perfect circulation, an atmospheric machine of terrifying beauty. But no machine, not even nature's most efficient, can run forever. By nightfall, Helena begins to weaken. As it moves inland, it loses contact with its power source, the warm ocean. Cut off from heat and moisture, the hurricane's internal balance collapses. Its winds slow, the eye fills with clouds. The roar fades to a howl, then to rain, then to silence. The storm that had drawn its strength from the sea dies of thirst on land. In its wake lies ruin, a coastline remade, a city once more underwater, a reminder that for all our technology, for all our models, we still live at the mercy of the sea. As rescue teams move in, one scientist mutters what many are thinking: this isn't just another hurricane. This is the future arriving early. And somewhere, far beyond the horizon, the next storm is already forming. A ripple of heat rising over Africa, invisible, inevitable. Because hurricanes are not isolated events. They are symptoms of something deeper, something global, a planet whose balance is shifting. Part 6, Aftermath and Autopsy. What the storm leaves behind: morning comes, gray and quiet. The sky, once a furious swirl of motion, is still again, a blank, washed-out canvas stretching over a broken world. The air smells of salt, diesel, and wet wood. Streets have turned to rivers. Boats rest where houses once stood. Cars lie stacked like toys against telephone poles. Hurricane Helena has moved on, limping inland as a downgraded tropical storm. But in its wake, it has left a scar that stretches for hundreds of miles. A scar written in shattered glass, splintered wood, and silence. In the city of New Orleans, rescue helicopters sweep over neighborhoods that only yesterday were alive with the hum of life. Now, rooftops jut above brown water like tombstones. People wave makeshift flags from their attics. The heat returns quickly. The smell of decay begins to spread. The power grid is gone. Cell towers toppled. Roads impassable. The city is once again an island, cut off from the outside world, suspended between flood and sky. Inside a temporary command center at Louisiana State University, meteorologist Robert Rogers and his team begin their grim task, analyzing what happened. The process is called a post-storm autopsy, a scientific dissection of the hurricane's life cycle from genesis to decay. They start with the data, pressure readings, wind speeds, satellite imagery, drops on telemetry. Every byte of information recorded during Helena's rampage is compiled and time-stamped, forming a digital fingerprint of the storm. Rogers scrolls through the graphs, shaking his head. The intensification rate was beyond anything we've ever modeled. It jumped 20 millibars in 6 hours. That's not supposed to happen. The term for this phenomenon is rapid intensification, when a hurricane's wind speed increases by at least 35 miles per hour within 24 hours. It's the nightmare scenario for forecasters because it leaves little time to warn the public. In the past, such rapid surges were rare. Now they're becoming common. Across the room, Joe Sion reviews data from the boundary layer drones, the small autonomous planes that had flown into the storm's lower altitudes. Their readings reveal a disturbing detail. The ocean beneath Helena was unusually warm, but more importantly, it stayed warm even as the storm churned overhead. Normally, hurricanes cool the ocean's surface as they pass, stirring up colder water from below. But this time, the warm layer was deep, extending more than 150 feet down. The storm never ran out of fuel. That's the signature of climate change, Sion murmurs. The ocean's heat content is increasing, not just at the surface, but throughout the upper layers. It's like giving the storm an endless gas tank. Meanwhile, the engineers begin to assess the human cost. The U.S. Army Corps of Engineers maps the breaches in the levee system. They find 2 major failures, both caused by overtopping rather than structural collapse, meaning the walls held, but the water simply rose higher than expected. Every design assumption we had, one engineer admits, was based on the past. But the past isn't the baseline anymore. In the hurricane's path, more than 2,000 homes have been destroyed. Power outages stretch from Baton Rouge to Mobile. Economic losses are measured not in millions, but in billions. But beyond the human suffering, scientists see Helena as a message, a warning carved into the coastline. Each hurricane is a data point in a growing pattern, and the pattern is clear. The storms are getting stronger, wetter, slower. Dr. Forrest Masters' team at the University of Florida examines footage from their hurricane simulator, a machine capable of reproducing 150-mile-per-hour winds. Their tests show how modern homes fail. Not from total collapse, but from small breaches, a window, a garage door, that allow pressure to build until the roof peels away like paper. It's death by design flaw, Masters says. We can't stop the wind, but we can design smarter. We have to build for the storms we're getting, not the ones we remember. Elsewhere, oceanographers analyze the surge data. Instruments along the Mississippi coast recorded sea levels rising 27 feet, the highest ever measured in the continental United States. That's not just a record, it's a revelation. Stephen Baig, the veteran surge modeler, looks grim as he overlays the surge map with population data. It's simple math, he says. Warmer oceans, higher seas, stronger storms. The coastline is shrinking, and the danger zone is expanding. But for all the damage, there is also awe. From the scientist's perspective, Helena is a perfect case study, a natural laboratory for understanding how extreme weather behaves in a warming world. They will spend months parsing the storm's anatomy, comparing radar snapshots, reconstructing wind fields, and feeding new insights into global models. And yet, there's an unease in the air, a sense that the data tell only part of the story. Because Helena is not an isolated event. It is a symptom of something larger, something planetary. Over the past few decades, the number of Category 4 and 5 hurricanes has risen dramatically. At the same time, ice sheets are melting, ocean currents are shifting, and the jet stream is behaving in strange, unpredictable ways. Earth's climate system, once self-regulating, seems to be entering a period of instability. Some scientists call it climate turbulence. the point at which feedback loops begin to amplify themselves. More heat leads to more evaporation. More evaporation leads to stronger storms. Stronger storms churn the ocean and release even more heat. It is, in a way, a planetary version of the hurricane's own mechanism, a feedback engine without brakes. Standing among the wreckage, Chris Landsat sums it up quietly. Every hurricane tells us something about where the planet is headed. The question is, are we listening? The sun breaks through the clouds over the ruined city, turning the floodwaters into a mirror. Reflected in it is a truth as old as the earth itself, that destruction and creation are twins. From chaos, new patterns emerge. From disaster, new understanding. But understanding alone may not be enough, because far beyond this drowned coast, in another corner of the planet, the climate's next great test is already written in stone. A story of a world that froze solid, of an Earth that once nearly died. And if the lessons of Helena are ignored, we may find that history has a way of repeating itself, not as myth, but as memory. Part 7, Snowball Earth. When the world froze solid, if hurricanes are the fury of a living planet, Snowball Earth is its silence. A time when the roar of storms gave way to a frozen stillness that nearly ended all life. It happened long before humans walked the Earth, nearly 650 million years ago. The continents were bare, lifeless expanses of rock. The air was thin and poor in oxygen, and the oceans, once teeming with microscopic life, began to turn to ice. What began as a cooling trend spiraled into catastrophe. The sun shone weaker than it does today, and volcanic activity slowed, reducing the carbon dioxide that trapped heat in the atmosphere. The planet's thermostat, a delicate balance between incoming sunlight and outgoing heat, tipped too far toward cold. Snow began to fall even near the equator. The oceans froze. Glaciers spread from pole to pole. Earth, the blue planet, turned white. To understand this ancient apocalypse, scientists have scoured the rocks of Namibia, Canada, and Australia, finding evidence of glacial deposits. The scraped, striated marks left behind by ice, in places that today lie in the tropics. The conclusion was inescapable. The entire planet had once been encased in ice. Dr. Paul Hoffman of Harvard University was among the first to piece together the story. "Imagine standing on a tropical beach," he once said, "and seeing glaciers grinding their way into the sea. That's the image that changed everything. In this global deep freeze, the oceans became sealed beneath a crust of ice hundreds, perhaps thousands of meters thick. Sunlight could no longer reach the water below. Photosynthesis stopped. The carbon cycle, the mechanism that regulates planetary temperature, came to a standstill. It should have been the end, and yet, somehow it wasn't. Deep beneath the frozen surface, life clung on. Near volcanic vents on the seafloor, bacteria fed on the minerals and heat rising from Earth's interior. These microbial survivors kept evolution's flame alive during the planet's coldest age. Meanwhile, above the ice, Earth's own geology began plotting its escape. Volcanoes, though fewer, never stopped entirely. Each eruption released carbon dioxide into the atmosphere, gas that could not be reabsorbed by the frozen oceans. For millions of years, the greenhouse gases built up. Eventually, they reached a tipping point. The same feedback that had once plunged the planet into ice now reversed. Carbon dioxide trapped heat. The glaciers began to melt. Sunlight reflected from the white surface was absorbed instead by the dark rock beneath. The thaw accelerated. In what geologists call the Great Melt, temperatures rose by tens of degrees in only a few thousand years, an instant by planetary standards. The ice vanished. The seas flooded back. Carbon levels soared to more than 300 times their modern concentration. The Earth had gone from frozen death to greenhouse fever. The scars of that transition are still visible today. Thick bands of capped carbonates, layers of limestone that formed as the oceans absorbed massive amounts of CO2 from the atmosphere. They are geological fingerprints of resurrection. Dr. Hoffman describes it as a planetary near-death experience. We almost lost the biosphere, but what came after changed everything. Indeed, The end of Snowball Earth marks the beginning of something extraordinary. The Cambrian explosion, the sudden diversification of complex life. From the ruins of the freeze came multicellular organisms, creatures with shells, eyes, and nervous systems. In short, life as we know it began after the greatest catastrophe the planet ever endured. It's a paradox that has haunted scientists ever since, that destruction and creation are not opposites but partners, each making the other possible. But as researchers study the conditions that led to Snowball Earth, a chilling pattern emerges. The forces that froze the planet were not random. They were the result of feedback loops gone wild, the same kind of runaway processes that modern scientists see echoing in today's climate data. Back then, it was cooling. Today, it's warming. But the principle is the same. Small changes in balance can lead to global transformation. Dr. Catherine Freeman, a geochemist at Penn State, warns, "We like to think the Earth is stable, that it resists change. But the record tells us it can swing from one extreme to another. If the climate system could freeze the planet solid once, it can certainly overheat it now. The parallels are hard to ignore. The same feedbacks that once amplified cold, ice reflecting sunlight, oceans absorbing less heat now amplify heat. Melting ice reduces reflection. Warmer oceans absorb more sunlight. More heat means more melting. A runaway loop in the opposite direction." In this way, Snowball Earth isn't just an ancient story, it's a mirror, a warning written in stone that shows how easily a planet's equilibrium can shatter. And in that mirror, scientists now see the faint outline of another world forming. A planet where heat, not ice, is the enemy. Where hurricanes grow faster, wildfires spread wider, and droughts stretch longer. A world where the feedback loops of energy and entropy begin once again to run unchecked. From the icebound silence of a frozen world to the roaring chaos of modern storms, Earth's message is the same. Balance is temporary, and survival depends on adaptation. But if the planet could come back from total ice, could it recover from total heat? That question, the one that haunted the frozen Earth, is now humanity's to answer. Part 8. Rebirth and Memory. How life returned after the ice. When the Great Thaw began, it must have been apocalyptic. The frozen crust of Earth cracked open, releasing torrents of meltwater that carved new valleys and flooded ancient basins. Entire mountain ranges shuddered under the weight of retreating ice. Volcanoes erupted in chains, painting the sky with plumes of ash and steam. And yet, from this violence came rebirth. As the glaciers retreated, they left behind a transformed planet, reshaped continents, newly formed oceans, and a chemical oceanic soup rich with nutrients washed from the rocks. For the first time in millions of years, sunlight reached the seas again. Photosynthetic organisms, algae, cyanobacteria, and other survivors of the long freeze seized the opportunity. They multiplied explosively, filling the oceans with oxygen and color. It was the dawn of renewal, the end of Earth's silence. Geologists call this period the Ediacaran, a bridge between the frozen desolation of Snowball Earth and the vibrant explosion of life that would follow. Fossil beds in Namibia and Australia show soft-bodied creatures appearing in abundance. Discs, fronds, and ribbons of strange, alien forms. They were unlike anything alive today, perhaps the planet's first experiments in multicellularity. Dr. Mary Drozer, a paleontologist at the University of California, Riverside, describes the Ediacaran seas as a world learning how to breathe again. You had these vast, shallow oceans full of nutrients from the melted glaciers, she explains. It was like the planet had been rebooted. Life was starting over, but with memory. That memory was chemical, encoded in DNA, the sum of every adaptation that had allowed life to survive the freeze. The microbes that endured near hydrothermal vents carried the genetic blueprints for resilience. When warmth returned, those blueprints became the foundation for complexity. And so evolution accelerated. Oxygen, once scarce, began to accumulate in the atmosphere. With it came the development of metabolism, organisms that could use oxygen to extract more energy from food. The stage was set for the emergence of animals capable of movement, sensation, and thought. To the scientists tracing these ancient signals, the story of Snowball Earth is more than a geological curiosity. It's a parable of transformation. Dr. Hoffman puts it simply, the Earth nearly died, and in dying, it learned how to live better. From the ashes of catastrophe, the biosphere reinvented itself. The new ecosystems were more diverse, more robust, and more interdependent than ever before. Complexity, it seems, was the planet's response to crisis. The parallels to our present moment are impossible to ignore. Today, as the Earth warms and ecosystems strain, humanity stands at a similar inflection point. Our technologies and societies are the modern equivalents of those ancient microbial networks, adaptive systems struggling to survive in a changing environment. The difference is that this time, the agent of change isn't volcanic or cosmic. It's us. We've become a geological force in our own right. The carbon we release rivals that of the supervolcanoes that ended the Ice Age. Our emissions trap heat with the same ferocity that once melted the planet's glaciers. Yet the lesson of the ancient thaw remains. Renewal is possible, but it comes at a cost. Every ecosystem that followed Snowball Earth was shaped by loss. Extinction paved the way for diversity. Chaos forced innovation. The survivors of the freeze were not the strongest, but the most adaptable. Those that could change their form, their metabolism, their strategy. For humans, adaptation takes a different shape. It means rethinking how we build, how we consume, how we define growth. It means designing systems, from cities to power grids, that can bend without breaking. In this sense, our species is at its own Ediacaran moment, emerging from the ice of ignorance into the warmth of understanding, still fragile, still learning what it means to survive a planetary transformation. The rocks remember. They record every cycle, heat and cold, extinction and bloom. And if they could speak, they might tell us that each age of catastrophe is also an age of opportunity. It was after the Great Freeze that life found the courage to grow eyes, to move, to think. Perhaps, after our own era of storms and heat, we too will learn something fundamental about resilience, about humility, about coexistence with the planet that birthed us. For now, we stand at the edge of that realization between knowledge and action, between survival and surrender. The same Earth that once froze itself into silence and then thawed back into song is speaking again. This time through melting ice caps, rising seas, and the howling wind of hurricanes. The question is no longer whether the planet can recover. It always has. The question is whether we will be part of its recovery, or just another layer in the fossil record. Part 9, Echoes of Extremes. Linking the past and the future history, it turns out, never really ends. It echoes across oceans, through rock, and even in the atmosphere above our heads. The patterns of catastrophe that shaped the ancient Earth are still alive today, only rewritten in a warmer script. When scientists look at the frozen sediments of Snowball Earth and the swirling clouds of modern hurricanes, they're seeing chapters of the same story. A planet that oscillates between extremes, forever searching for balance. Ice and fire, calm and chaos, two sides of the same planetary heartbeat. Dr. Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, puts it this way: the planet has always been changing. What's new is the speed. We're compressing geological change into a human lifetime. It's a chilling truth. In the distant past, the shift from icehouse to greenhouse took millions of years. Today, carbon levels are rising faster than at any time since the dinosaurs vanished. The feedback loops that once froze the planet solid are now accelerating in reverse. Melting ice, warming seas, fueling storms. The same physics that governed the glaciers of the Neoproterozoic now governs the hurricanes of the 21st century. Only the sign has flipped. Where the ancient world reflected sunlight away and froze, ours traps it and burns. The connection between those two extremes is the carbon cycle, Earth's ancient climate control system. Volcanoes and weathering once balanced the equation over eons, but human industry has rewritten the math. Every ton of carbon released from a smokestack or exhaust pipe tips the scale, just as volcanic gases once did. The consequences ripple outward. Warmer oceans feed hurricanes like Helena, intensifying them faster and pushing them further inland. Melting ice caps raise sea levels, turning storm surges into walls of water that reach places never before flooded. Shifting jet streams twist weather systems into new, unpredictable shapes. To some, these are isolated disasters, random tragedies of weather. To others, they are symptoms of a deeper planetary rhythm. Earth reminding us that energy, once unbalanced, always seeks a way to equalize. Dr. Catherine Hayhoe, a climate scientist and communicator, describes it bluntly: climate change isn't about saving the planet. The planet will be fine. It's about saving the systems we depend on, our homes, our food, our sense of stability. In that light, Hurricane Helena isn't just a meteorological event. It's a messenger, the atmospheric equivalent of a warning flare shot across time. The processes that powered it are the same ones that shaped Earth's ancient catastrophes. They're not supernatural, not mysterious. They're physics magnified by our own hand. And yet, there's a poetic symmetry in this. The same planet that froze itself nearly lifeless to reset evolution now heats itself feverishly, as though testing the limits of its latest creation, humanity. For the scientists who piece together these patterns, the comparison is more than metaphor. Geologists studying snowball Earth often speak with climatologists modeling future warming. Their datasets overlap in unexpected ways. Isotopic ratios, sediment compositions, oceanic circulation models. Each field informs the other. At MIT, Dr. Daniel Rothman has been studying the thresholds of planetary stability. He's found that when carbon levels rise too fast, faster than ecosystems can adapt, mass extinction follows. It happened during the Great Dying 252 million years ago, when volcanic emissions triggered a greenhouse crisis that killed 90% of life. It happened in reverse during snowball Earth. And Rothman warns, we may be approaching another such threshold today. It's a sobering symmetry. In the past, it took millions of years for ice to recede. Now, in mere centuries, we've melted glaciers that once seemed eternal. The echoes of extremes are growing louder, but within those echoes lies a strange kind of hope, the same resilience that carried life through the frozen eons. For every collapse in Earth's history, there has been a recovery. Every extinction has cleared the stage for reinvention. Humanity, for all its flaws, is part of that pattern. We are, in a sense, the planet thinking about itself, the product of eons of adaptation, now faced with the challenge of directing evolution consciously rather than reacting to it. Perhaps that is our role in the long narrative. Not to conquer nature, but to learn from its cycles, to recognize that survival depends not on dominance, but on understanding. When viewed through that lens, the hurricane and the glacier are no longer opposites, they're teachers. Both remind us that equilibrium is fleeting, and that every action, from the swing of a hammer to the breath of a storm, is connected. The climate models of today, like the rock records of the past, are messages from the same storyteller, the Earth itself. Its language is data, its syntax is time. And if we listen carefully, we can hear what it's saying. That the future we face is not unprecedented, but accelerated. That we've been here before, just more slowly. The question now is whether we can remember the lessons written in ice before they're rewritten in fire. Because the echoes are no longer faint. They're roaring, in the melting permafrost, in the rising seas, in the storms that now arrive with unnatural speed. The past is not past. It's repeating, faster, louder, and with us inside it. And somewhere, deep beneath our feet, the planet is keeping score. Part 10, The New Climate Age. A planet out of balance. Every age of Earth has had a name. The Archean, when the first continents rose from the sea. The Cambrian, when life burst into complexity. The Pleistocene, when glaciers carved the world we know. But geologists are now forced to add a new one that marks humanity's hand upon the planet. The Anthropocene. It is an age defined not by ice or fire, but by us. From orbit, the planet still looks serene. the same marble swirl of blue and white that astronauts once described as fragile. But beneath the atmosphere, the balance that sustained life for billions of years is shifting. And it's shifting fast. Carbon levels have climbed beyond 420 parts per million, higher than at any time in at least 3 million years. Ocean temperatures are rising in tandem, and with them, the violence of the atmosphere. The climate system that once moved with the patience of millennia now jerks and spasms in decades. In short, the Earth's thermostat has slipped. Dr. Shukuro Manabe, one of the pioneers of climate modeling, predicted this decades ago. His early simulations showed how carbon dioxide would trap heat unevenly, altering wind patterns and ocean currents. At the time, his warnings seemed distant, almost academic. Now, his models look less like predictions and more like maps of the present. Across the globe, we see the consequences unfold. In the Arctic, summer sea ice is vanishing faster than any model anticipated. In the Pacific, coral reefs bleach white in waves of underwater heat. In the tropics, cyclones grow larger, wetter, and more erratic. And in the mid-latitudes, droughts alternate with floods, rewriting the rhythms of agriculture that sustained civilization. The planet's great circulatory systems, the jet streams, monsoons, and ocean currents, are faltering like a heart skipping beats. Dr. Jennifer Francis at the Woodwell Climate Research Center describes it in one word: meandering. The jet stream used to flow like a steady river, she says. Now it bends and wobbles, trapping heat in some regions and cold in others. It's weather without memory, every year more unpredictable than the last. In this new climate age, boundaries blur. Wildfires burn through frozen tundra. Storms strike where storms never were. Ancient forests dry out and die in silence. And yet, the Earth is not dying, it's changing. The problem is that the speed of change now outpaces our ability to adapt. The great cycles of Earth once moved in harmony, self-correcting over time. Carbon absorbed by oceans, heat radiated into space, glaciers reflecting sunlight to cool the poles. But human intervention has thrown those feedbacks into chaos. We have overwhelmed the natural regulators. The atmosphere, in response, has begun to speak in new dialects of disaster. Hurricanes like Helena are one of those dialects. So are megafires in Australia, heat domes over Europe, and rivers running dry in South America. Each is a sentence in the same planetary conversation, one that says, in essence, you have altered the balance. And yet, amid this sobering reality, a new kind of science is emerging, one not just of observation, but of restoration. In Iceland, engineers are injecting captured carbon into volcanic rock, turning greenhouse gas into stone. In Kenya, solar-powered desalination plants turn seawater into drinking water, giving life back to arid land. In Louisiana, the very coastline that Helena ravaged is being rebuilt through controlled river diversions, letting the Mississippi resculpt its delta as it once did naturally. Dr. Kate Marvel, a climate physicist at Columbia University, calls this shift planetary maintenance. We can't undo what we've done, she says, but we can learn to work with the system again, to listen to its feedbacks instead of ignoring them. Still, the task ahead is immense. The forces we've set in motion have inertia, oceans that warm slowly, glaciers that melt for centuries, carbon that lingers for millennia. Even if emissions stopped tomorrow, the atmosphere would continue adjusting, perhaps violently, for generations. This is the paradox of the Anthropocene. We have become both the stewards and the saboteurs of the same world. And yet, there's a quiet hope in this acknowledgement. To name an age after ourselves is not just an act of guilt, it's an act of responsibility. It means we finally see that we are not apart from the Earth, but part of it, and accountable to it. The new climate age is not a punishment. It's an invitation to evolve again consciously this time. To rediscover balance not through catastrophe, but through intention. Because the truth is simple, if unsettling, the Earth will find equilibrium again. It always does. The only question is whether that equilibrium will include us. The storms, the droughts, the melting ice. These are not omens of an ending, but signals of a transition. The same kind of transition that once froze the world and thawed it back to life. Perhaps thousands of years from now, geologists will read our layer in the rocks, the plastics, the soot, the radioactive traces, and call it what it was. The moment the planet became self-aware of its own fragility. A warning written in carbon. A second chance disguised as a crisis. The balance is broken, yes, but it is not lost. Not yet. Part 11. Signals from the future. What the next century could bring. The future, in climate science, is never singular. It branches. Each path is a simulation, a possibility written in equations and probabilities. A series of what-ifs that stretch across the next 100 years like diverging rivers. In the halls of the Intergovernmental Panel on Climate Change, IPCC, in Geneva, scientists call these representative concentration pathways, RCPs for short. Each represents a version of our collective destiny, measured by how much carbon humanity releases into the air. RCP 2.6, a future of restraint. RCP 4.5, a world of compromise. RCP 8.5, the path of abandon. Which path we follow will determine not just temperatures, but tides, storms, and survival itself. At first glance, the differences seem subtle, a few degrees here, a meter of sea level there. But the truth lies in the scale. The Earth's average temperature, like the human body's, operates within narrow limits. A 2-degree fever changes everything. Dr. Michael Mann, one of the world's leading climatologists, puts it bluntly, 2 degrees is not a line we can cross safely. It's a cliff. The closer we get, the steeper the fall. Already, we are halfway there. Computer models project that, without drastic change, the 21st century will see an average rise of 3 to 4 degrees Celsius. It sounds modest, the difference between a warm and a hot afternoon, but averaged across oceans, forests, and cities, it reshapes entire ecosystems. In that world, the Arctic becomes ice-free in summer. Coral reefs vanish. The Amazon, once the lungs of the planet, dries and burns, releasing more carbon than it stores. Hurricanes grow stronger, droughts linger longer, and coastlines recede into the sea. In South Asia, heat waves surpass the threshold of human endurance, 50 degrees Celsius wet bulb temperatures that make survival without cooling impossible. In North America, megafires carve new deserts from once green landscapes. And across the equator, millions are forced to migrate, not from war or politics, but from the slow violence of heat. Yet amid these projections lies a second truth. The future is not a sentence, but a story still being written. Because even as the models warn of catastrophe, new tools of resilience are emerging. Cities are beginning to evolve. In Rotterdam, engineers have built floating neighborhoods, modular homes that rise and fall with the tides. In Singapore, vertical farms transform skyscrapers into food sources. In Morocco, solar arrays stretch across the desert like metallic seas, generating power for millions. And in the American Midwest, experimental carbon farms use enhanced soil microbiomes to capture atmospheric CO2, restoring fertility while reversing emissions. It's as though humanity, sensing the danger, has begun to awaken the same instinct that saved life after Snowball Earth: adaptation through innovation. Still, adaptation has limits. For every success story, there are those left behind. Island nations like Kiribati and Tuvalu are already preparing for exile, negotiating to relocate entire populations as their homelands vanish beneath the rising Pacific. It's the first wave of what some call climate refugees, a term that will soon lose its metaphor. Dr. Salim Ul-Haq, a Bangladeshi climate scientist, once said, "In the coming century, migration will be adaptation." His words carry both pragmatism and tragedy, a recognition that survival may no longer mean staying put. The Earth of 2125 could be a patchwork of resilience and ruin, cities shielded by seawalls and powered by clean energy, surrounded by regions struggling under drought and displacement. In some places, technology will triumph. In others, nature will reclaim what was taken. But the most profound transformation may not be physical, it may be philosophical. For centuries, humanity has seen itself as separate from nature, as master rather than participant. The storms and the ice have always been reminders that this illusion cannot hold forever. Already, a new consciousness is emerging, one that treats climate not as a backdrop, but as a living system of which we are a part. Schools teach children to read carbon maps like constellations. Architects design not against weather, but with it. Even language evolves, sustainability, giving way to symbiosis. Perhaps this is what it means to enter a new epoch. Not the end of the world, but the end of the old way of seeing it. Still, the choices of this century remain stark. Follow the high-emission path, and the storms of Helena's scale will become yearly, not generational. Seas could rise by 2 meters or more, erasing cities from Miami to Mumbai. The great ice sheets of Greenland and Antarctica could pass their points of no return, locking in centuries of flooding. But choose restraint, commit to deep cuts in carbon, massive reforestation, and sustainable energy, and the worst can still be softened. The fever can break. The balance, though fragile, can be restored. Dr. Katharine Hayhoe, in her lectures, often reminds her audiences, the most dangerous myth is that it's too late. It's never too late to make a difference, only too late to make the same difference. The signals from the future are clear, but not final. They are warnings, not prophecies. The world we inherit in the next century depends on the one we imagine today. The question, as always, is whether imagination can outpace inertia, and whether, when the next great storm rises from the sea, we will still be counting its damage or measuring our understanding. Part 12, The Turning Point, Science, Survival, and the Human Choice. There are moments in history when the story of a species bends, moments when knowledge meets necessity, and the future balances on a knife's edge. For Earth, that moment is now. Every hurricane, wildfire, and melting glacier has brought humanity to a single realization. The climate crisis is not a distant horizon. It is the present tense of our civilization. And unlike the natural cycles of the past, this one is written by human hands. In laboratories and observatories around the world, scientists race not only to understand the changes but to counteract them. They have become both witnesses and engineers of the planet's next chapter. In Switzerland, at the CERN research facility, physicists have begun studying how cosmic rays influence cloud formation, exploring whether subtle shifts in Earth's upper atmosphere could change rainfall patterns. In Hawaii, the Mauna Loa Observatory continues its unbroken record of measuring atmospheric carbon, a dataset stretching back to 1958, the planet's pulse, rising year by year. Meanwhile, at the Scripps Institution of Oceanography, oceanographer Ralph Keeling, son of the man who began that record, describes the challenge with quiet resignation. We are watching the atmosphere change in real time. It's like standing beside a patient whose condition worsens slowly, predictably, and knowing exactly why. But alongside the data comes innovation. Renewable energy, once a niche, now outpaces fossil fuels in growth. Wind farms stretch across plains once thought barren. Offshore turbines rise from the North Sea like white sentinels. Solar arrays bloom in deserts from Nevada to Namibia, their mirrored panels tracking the sun like mechanical sunflowers. Carbon capture technologies, the dream of removing what we have released, are no longer fiction. In Iceland's Hellisheidi geothermal plant, machines inhale air and strip away CO2, injecting it into volcanic basalt where it mineralizes into stone. The process mimics nature's own chemistry, sped up by human design. And yet, technology alone will not save us. Dr. Elizabeth Kolbert, Pulitzer-winning author and climate journalist, writes, "We are tinkering with the very systems that make life possible. Our genius has always been to solve problems. The danger is that we now create them faster than we solve them. The true turning point, many scientists argue, will not be technological but psychological, the moment when collective awareness transforms into collective will. Because while climate change is a planetary problem, its roots are profoundly human. consumption, inequality, denial, delay. The solutions, too, must be human cooperation, empathy, foresight. In a small village in Bangladesh, families elevate their homes on stilts to withstand rising floods. In California, firefighters train artificial intelligence systems to predict wind shifts in real time. In Norway, engineers design highways that charge electric cars as they drive. Each of these acts, local, specific, imperfect, is a thread in a global web of resilience. The question is whether the threads can be woven fast enough to hold. Back in Louisiana, where Hurricane Helene's scars remain raw, a new generation of meteorologists is rising. They grew up watching storms that defied old rules, oceans that warmed without pause. Many of them chose their careers not out of curiosity, but necessity. When asked what drives her research, 27-year-old atmospheric scientist Leila Moreno doesn't hesitate. I study hurricanes because I don't want my children to fear the ocean. I want them to respect it, to understand it, but not to see it as an enemy. Her words echo what might be the defining truth of this century. Survival will depend not on domination of nature, but on reconciliation with it. Human history has always been a dialogue with the planet. The glaciers teaching patience, the deserts teaching endurance, the storms teaching humility. For the first time, though, the conversation is two-sided. The Earth responds now, visibly and immediately, to our choices. It is no longer a backdrop. It is a participant. At the United Nations Climate Summit, leaders debate targets and timelines: 2050, 2070, net zero, carbon negative. The language is clinical, the politics exhausting. But outside the conference halls, the world is already speaking in clearer terms. Through rising seas in Jakarta, wildfires in Greece, droughts in Kenya, and the accelerating thaw of Greenland. Those are not projections. They are messages. And yet, if there's one thing the story of Earth has shown, from snowball to Helena, from ice to heat, it is that life endures. Always. The turning point, then, is not a single decision, but a continuum, a series of moments when understanding becomes action. Each choice, each innovation, each refusal to look away nudges the balance back toward stability. There will be more storms. There will be more floods. But perhaps, if we listen, truly listen, they will no longer be warnings. They will be reminders. Reminders of what the planet can survive, and of what we can become if we choose to survive with it. Part 13. The Age of Understanding. Humanity's place in the planet's story long before humans ever measured a temperature or named a storm. The Earth already knew how to change. It breathed through ice ages and fire, expanded and contracted like a living organism. But now, for the first time, that awareness has passed to us. The species capable of looking back through deep time and realizing we are part of a continuous story that began billions of years before our arrival. Our technologies mimic the planet's own systems. Solar panels capturing light like leaves, desalination mimicking cloud formation, carbon capture resembling the slow breathing of forests. For the first time in history, our inventions echo the wisdom of nature. In classrooms from Nairobi to Oslo, children learn about climate not as catastrophe, but as ecology, a relationship. They grow up planting mangroves to hold back the sea, coding algorithms that optimize wind farms, and restoring wetlands that once were drained. To them, stewardship is not sacrifice. It's identity. It's this generational shift, quiet, patient, global, that defines the age of understanding. Because while politics lags and economies cling to the old world, culture is evolving faster. Artists, filmmakers, and storytellers now frame the planet not as backdrop, but as protagonist. Every painting of a burning forest, every poem about rising seas, is a small act of empathy, a reminder that the planet's fate is also ours. The philosopher Bruno Latour once wrote, "We have never been modern, only forgetful." He meant that progress, as we defined it, was an illusion of separation. We built towers and cities, engines and empires, believing we had transcended nature, when in truth we had only misplaced our belonging. The Age of Understanding is about reclaiming that belonging. It's the realization that the same forces that carved canyons and raised mountains also circulate through our lungs. That the carbon we burn was once living sunlight. That the line between the human and the natural has always been an illusion. In the ruins left by hurricanes like Helena, in the fossils of snowball Earth, in the thin blue glow of atmosphere seen from space, the message is the same. We are temporary caretakers of a permanent home. And home is not something to be conquered, it's something to be remembered. In a sense, the Earth has always been teaching, through its storms, its silences, its slow, cyclical rebirths. We are only now learning the language. At the dawn of this new era, science and spirituality, reason and wonder are converging again, not as opposites, but as partners. We measure the carbon in the air, yes, but we also feel the weight of it. We map the melting ice, but we also mourn it. And in that dual awareness, the analytical and the emotional, lies a maturity the planet has never seen before. It may not be enough to stop what has begun, but it may be enough to guide what comes next. For if the last great transition from snowball Earth to the Cambrian bloom gave rise to complexity, then perhaps this one will give rise to conscience. A species capable not just of survival, but of wisdom. And maybe millennia from now, when the storms have quieted and the seas have settled, someone or something will look back at this age and call it what it truly was, the moment when the planet woke up to itself. Part 14. Echoes of Tomorrow. The legacy of the storms. The storm always passes. The sky clears, the winds fall silent, and the world begins the slow work of remembering. But memory, like weather, is never static. It shifts, fades, resurfaces, an echo that lingers long after the waters recede. Centuries from now, when our cities have turned to dust and our satellites orbit as relics, what will remain of us? Perhaps not our monuments, nor our machines, but the marks we left on the planet's rhythms, the carbon in the air, the plastic in the sediment, the scars of hurricanes on a reshaped coast. These will be our fossils. And yet, even those traces will become part of Earth's next chapter. The planet is, after all, a master of recycling its own past. Every mountain was once seabed. Every storm leaves minerals that feed new forests. The wreckage of one age becomes the raw material of the next. In that sense, the legacy of our storms, both literal and metaphorical, is not destruction but transformation. Dr. Sylvia Earle, the oceanographer sometimes called her deepness, once said, "The ocean is resilient, can recover if we give it the chance. The question is not whether the planet can heal, it's whether we will allow it to." She's right. Already, the early signs of recovery are visible. In coral nurseries off the coast of Belize, scientists cultivate fragments of reef that once seemed doomed, replanting them into restored ecosystems. In the Arctic, projects to reintroduce lost tundra species, from mosses to bison, are stabilizing permafrost and slowing thaw. These are small acts in a vast equation, but each one is an echo of responsibility. Because just as every storm begins with a breath of warm air, every act of restoration begins with a single choice. In Louisiana, where Helena's name has joined the long list of hurricanes etched into history, the coastline is being remade, not by concrete barriers, but by sediment, water, and time. The Mississippi River, long imprisoned by levees, is being allowed to spill into the marshlands again, building new deltas from its own flood. It's a return to the wisdom of the wild, to the idea that working with nature is stronger than resisting it. And slowly, the landscape changes. Saltwater retreats, birds return, new grasses root in the silt where houses once stood. Helena, like Katrina before her, has become both a wound and a teacher. In classrooms around the world, her name is now shorthand for more than disaster. It stands as a case study in adaptation, a reminder of how human innovation and planetary resilience can intertwine. The data gathered from her formation, the dropsondes, the satellite imagery, the deep ocean readings, continues to shape modern hurricane prediction. Each storm we survive teaches us how to endure the next. Even the worst tempests leave knowledge in their wake. That may be humanity's most enduring gift, the ability to learn from pain, to turn chaos into understanding. Where the planet destroys, it also instructs. Where it floods, it reveals what should not have been built. Where it burns, it clears the ground for renewal. This interplay of loss and learning has always driven evolution. After Snowball Earth, the glaciers melted, and life returned stronger, more complex. After every mass extinction, new forms arose, more adaptable than before. Perhaps we are now part of that same cycle, a civilization being forced to evolve not biologically but consciously. And though the age of storms is far from over, their legacy may yet be hope. Because storms, for all their fury, are agents of balance. They move heat from equator to pole, circulate nutrients, shape coastlines, stir oceans. Without them, the planet would stagnate. Their violence is also their purpose. In this way, the hurricanes of our century, Helena, Maria, Haiyan, Ida, are not just warnings, but vital expressions of a living Earth in flux. They remind us that stability is never permanent, that life thrives on change, that chaos itself can be a form of renewal. Perhaps this is why, even in their aftermath, there's beauty. In the stillness after the wind, in the silence of flooded streets reflecting the dawn, in the first green shoots pushing through the mud. The echoes of tomorrow are already here, whispered through the rising winds and quiet recoveries. They say, we are not separate. We are part of the same storm. And as the next generation of scientists, builders, and dreamers rise, they do so not to conquer nature, but to harmonize with it. The next era of human progress may not be about expansion, but about belonging, about finding our rhythm again in the great breathing of the world. In the archives of the future, when humanity's story is read through the sediment layers of our choices, perhaps it will not end with a warning, but with a realization that we were never the storm's victims, nor its masters, only its students. And that in learning from the wind, we finally learned to listen to the earth itself. Part 15, Final Silence. The planet remembers, the storm is gone. The winds that once tore the world apart now whisper through broken trees. The ocean has returned to its slow, rhythmic breathing. And above it all, the sky, endless, quiet, forgiving, stretches as if nothing ever happened. But the earth remembers. Every event, every storm, every heartbeat of the planet leaves its trace. In sediment, in ice, in the chemistry of the air. Geologists call it the stratigraphic record, a library of moments pressed into stone. Long after our cities crumble and our languages fade, these layers will remain, telling future eyes who we were and what we did. If those future observers could read the rocks the way we read words, they would find the story there. The warmth of the Anthropocene burned into isotopes of carbon, the brief fever of civilization marked by ash and plastic, the pulse of hurricanes like Helena etched into coastal sands. They would see how we pushed the atmosphere, how the oceans rose, and how, against all odds, life endured. Because even in its quietest hours, Earth is never still. It listens, records, adapts. It carries our actions forward in the chemistry of its rain, the dust of its mountains, the salt of its seas. The planet remembers not with judgment, but with fidelity. It has seen empires rise and vanish. It has worn continents as passing scars. It has been fire and ice, cradle and tomb. And through every transformation, life has always found a way to begin again. Perhaps that is the greatest truth of all, that renewal is built into the fabric of the world. In a field in Louisiana, where Hurricane Helena made landfall, grass now grows where houses once stood. The soil is rich with minerals carried by the flood. The wind that once destroyed now spreads seeds. Nature, unbothered by tragedy, continues the only story it has ever known, growth. Nearby, a child stands at the edge of a marsh, watching the water ripple under a sunset sky. She's too young to remember the storm that changed her city, but her parents told her about it. How the winds howled, how the sea came inland, how afterward the stars felt closer than ever. She doesn't know the science of hurricanes or the mathematics of climate, but she feels something older, an instinct that the Earth is alive, that it speaks, and that we are part of its voice. That instinct, simple and profound, may be the key to our survival. Because what began as a scientific understanding, a recognition of cycles, patterns, and systems, must become something deeper, a reverence. To know the Earth is not enough. We must remember it, honor it, and listen when it speaks through wind, water, and silence. The scientists who study the planet often talk about baselines, reference points from which change is measured. But perhaps the truest baseline is not in numbers or models. It's in memory, the memory of how the world once sounded when we were still in harmony with it. The whisper of waves, the hum of insects, the rhythm of rain on stone. That memory is fading, but it is not gone. It's carried in the stories we tell, the lessons we teach, the choices we make each day. From the frozen ages of snowball Earth to the heat-driven storms of our century, the planet has taught one lesson again and again. That balance is fragile but possible. That life's continuity depends not on control, but on coexistence. In the end, our story is the planet's story, an echo of its longing to know itself, to reach awareness through us. And if we listen closely, even now, we can hear it breathing, slow, vast, patient. The heartbeat beneath the noise. The rhythm that began long before us and will continue long after. Maybe one day, far into the future, when the next civilization looks upon this world, they'll find the traces we left, not just of destruction, but of awakening. They'll see that, in our final moment of crisis, we began to understand.